Hello. Today, we will be explaining what metastasis is. In order to understand what metastasis is, it is important to know what cancer is. Cancer is a disease caused by the uncontrollable growth and spread of abnormal cells in the body. Here, we see both a normal cell and a cancer cell. Normal cells come together to create tissues like your skin, heart, or bones. Cancer cells, however, come together to create a tissue called a tumor. And this tumor or tissue is made up of only cancer cells. Metastasis is the life-threatening spread of cancer cells from their origination site to other parts of the body, creating secondary tumors found in different places than the origination site, and these are spread using either the bloodstream or the lymphatic system. If you didn't know, the lymphatic system is a network of vessels that drain a fluid called lymph in the body. Whether metastasis uses the bloodstream or the lymphatic system is dependent on the origin and location of the primary tumor. For example, bone and soft tissue tumors are primarily spread through the blood, while melanoma, breast cancer, lung cancer, and gastrointestinal tumors are spread through the lymphatic system. For this video, however, we will be focusing on the bloodstream being the main route for metastasis, since it is the most common. There are 5 steps of metastasis, and these steps are usually called the metastatic cascade. The first step is invasion, the second is intravasation, the third is survival, the fourth is extravasation, and the fifth is outgrowth. Invasion is when cancer cells break free from the primary tumor and enter the bloodstream. Cancer cells can create enzymes that break down the extracellular matrix of the cells. And this matrix gives cells their structure and helps them attach to their neighbor cells. So when this matrix is broken, cancer cells are free to break away from their neighbors and move around the body. Here we see these 2 cancer cells breaking away from their neighbors of the primary site. I'm going to quickly demonstrate how this is done using imagery. For our instance, the enzymes are going to be green dots. So the first step of invasion is the cancer cells creating the enzymes, and the enzymes are going to invade the basement membrane and the proteins in the extracellular matrix, which is what these gray lines are. So the cancer cell makes the enzymes break through this matrix and these proteins, and then the cancer cell is free to move into the blood vessel. And once it's in the blood vessel, it goes to intravasation step. Another way to think about this is to think about a group of people standing in the same closed room of a house. So one person decides to break free, so they break through this door. This door is now open, and the person decides that they want to leave through the door they just broke. Now they are free to move anywhere in the house that they would like. In this analogy, the room that everyone started in is equivalent to the primary tumor. The door that the person broke down is equivalent to the basement membrane and the extracellular matrix that was broken down by the enzyme. The rooms of the rest of the house are equivalent to the rest of the body. Just like in the analogy, when the invasion step is complete, cancer cells are free and ready to move away from its primary site.
So at this point, the tumor has freed itself from the surrounding connective tissue and needs to move to a new location. And how it's going to do this is by a process called intravasation. And the very word itself gives us a hint. Intra meaning into, and vasation standing for vascular. And so together, these are going to be the movement into the vascular system where it will then go around. So there's different parts of this. Is going to be the movement itself. How are these cells physically moving along? The next is going to be direction. How do they know where or what direction they're going in? And then crossing into the actual blood vessels themselves. And so down here, just give you a quick rundown of the structure. These are what we call basal lamina cells. They protect this vasculature system that we have going on here. These orange particles are just to show the flow of nutrients. And then the blue is going to be the extracellular matrix on the outside of that blood vessel wall that sort of insulates and protects those cells. And so for the first question of movement, how do we go from point A to point B in these cells? And the answer is actually quite interesting. It's by a process called amoeboid movement. Inside the cell itself, you have these little skeletons, the cytoskeleton, that the cell uses to control the integrity of the wall that's surrounding them. But what they'll actually do is they will use their cytoskeleton to extend a little, what they call a foot. So they'll extend this out, that sort of then pulls this main body along and ultimately goes from point A to point B. So the cell itself will like stretch out as this with the intermediate, so the nuclei will move along with the rest of the cell. So we've got this amoeboid movement that puts us in the, ability to move, but how do they know what direction? And you can imagine it's sort of like you're receiving sunlight, or you can feel the sunlight on your face. These cells sense that there's a low concentration here in this area, and that there is a much higher concentration of these signals. It could be hormones, it could be nutrients, and they're going to then use their amoeboid movement over here to go towards this blood vessel wall. So that is how they know where to go. But then they've still got this whole area to get through. They got this great wall to sort of traverse. And how they do that is as this tumor cell, this black tumor cell, approaches the extracellular matrix, they will secrete enzymes here. And the purpose of these enzymes is to absolutely erase this extracellular matrix. It breaks it down. The ECM being made of sugars and whatnot, they can dissolve readily. And so now we have this cell that can move right up on that blood vessel wall. But there are these stitch proteins that sort of hold this blood vessel junction, this tight junction between these cells together. And so what the cell then needs to do is secrete a different type of enzyme. They could also potentially bind over here, and then there will be a cascade of activity that causes these to dissolve. So they dissolve those stitches, they sort of come through here, and then they will dissolve the stitches, this area that will then allow the cell to leak through, where it will then enter the blood cell, the bloodstream itself. And there you have it. Movement, direction, and crossing. Movement like a foot or an amoeba, direction by the sensing of these signals, and then the crossing of the body cell into the blood vasculature.
Okay, so now that the cell is in the vein, it has to survive until it can leave. So it's going to stay in this blood for a while. As I've shown here, the blood is composed of three major components. We have our red blood cells, represented by the red blocks, the platelets, represented by the orange ones, and the white blood cells, represented by the gray and white ones. While our cancer cell is in the blood, there are two primary dangers: the extreme forces applied to the cell and the immune system. An appropriate metaphor for the cell going through, let's say, the heart, would be the equivalent of a human going over the Niagara Falls without a barrel. It's going to be tossed and turned this way and that, and it's extremely likely that the cell is going to be torn apart just by the forces involved. Plus, there can be some collisions with various cell types, which can lead to deformation of our cancer cell and loss of functionality, which of course kind of prevents the whole point of metastasis. In addition to this, the other big danger is that cancer cells are actively being targeted by the immune system. Immune cells, like these white blood cells, their goal is to bind to cells that are considered abnormal, like our cancer cell. And when it binds, it's going to cause a reaction that's going to destroy our cell. And when the cell is destroyed, it will end up looking a bit like this: just a mass of random proteins that don't really have a point anymore. And because of that, can't really cause cancer. So this cancer cell, in order to survive this trek, has to avoid these white blood cells. One way that this can happen is by these platelets. The platelets typically can conglomerate into groups just naturally. And these cancer cells, what they can do is sometimes use that to their advantage. They will stick to some of these platelets, and more will stick on the edges. And this kind of camouflages our cancer cell as it moves through the blood. And when it's camouflaged like this, one, it's protected from collisions from other cells because the platelets are going to take the brunt of that damage. And the white blood cells can't recognize the cancer cells, so they're not going to destroy it. That's one of the main ways that our cancer cells have been shown to not be destroyed during its time in the circulatory system. There are other ways, but most of them are pretty poorly understood at this time. So while many of our cancer cells will die, some of them make it and survive long enough to move on to the next step.
All right, at this point, we've gone and covered how they get into the blood vessels and how they survive in the blood vessels, but we haven't talked about how they get out of the blood vessels, which is essentially the meaning of extravasation, or exiting the bloodstream. So what we're talking about here, these are going to be the three major factors contributing to this overall activity: coagulation within the bloodstream, recognition and compatibility with the wall of a blood vessel, and then invasion or crossing over of that arterial blood vessel wall. The coagulation portion of this is acquired inside of the bloodstream. So as these cells are ripped along by the strong currents and forces within this bloodstream, they're going very fast. There's not really a lot of an opportunity for them to, come along and attach to this side of the wall. But as they're moved around, they actually will come into contact with these platelets. These are platelet particles inside of the blood, and they dominate the process of coagulation for, to stop bleeding as well. But they do offer some clotting effects inside of the bloodstream under normal circumstances too. So they will actually coat the outside of this cell as it's moved along, which will then allow that cell to associate with any, major platelet blockages that are already formed on the arterial wall. That's enough to slow it down and get it into close proximity with that blood vessel wall. From there, it's pretty simple. Different parts of the blood vein or vasculature will be coated with different signaling molecules. So in this case, i.e. the brain tissue will excrete the green particles, whereas the brown particles are linked to the liver. So it's not like this cell is gonna, be able to recognize the brown particles without those proper cellular receptors on the surface of the tumor cell, but it already has the green receptors expressed on the outside, which then associate in a better portion with the green wall side of this tissue tropism. And that's going to be how it specifically recognizes where it should stop inside of the blood vessel. Now, from there, the tumor cell has attached to the wall through its tissue tropism activity with these receptor molecules over here. But now what you notice is that it doesn't necessarily know where to cross over. How it knows where to cross over is through a similar mechanism for how it knows where to cross over into the blood vessel, which is where these chemoattractant little chemical molecules are down here. They're going to be highly concentrated in some areas, and the cell will be able to sense that in a similar manner through the expression of some of these little proteins on the outside that are attracted to it. So it will actually roll and extend across the surface of this blood vessel towards an area of that highly concentrated chemoattractants. So we've bound to the cell wall, and we now know where to cross over. And it can do that through a variety of mechanisms. The first one is going to be very simple. If it sits on the cell wall long enough, it will actually just erase and kill these cells entirely. The point being that it's not perfect, but if they sit there long enough, they can degrade or induce killing on those cells. The other one is going to be the one we're more familiar with, where they secrete these degrading compounds that destroy those tight junctions and open up a wall in the cell where they will then see more of those particles fill that gap. From there, the outside surface coating proteins of the cell are attracted to these signals, and then you see the extension of this foot right in this area. But what that means is this is actually going to extend across that blood vessel barrier, which then the rest of the cell will follow suit and sort of leak through or slink through this hole in the blood vessel wall until it is located now in the peripheral tissue, matching the tissue that it was looking for. All in all, we have covered now the coagulation of the cells to the arterial side wall or the vascular side wall. It recognizes specifically where it should attach to, and then it will look for the best route to cross over, either through a chemoattractant signal on this left side, or just by sitting here long enough and completely erasing everything in front of it. In the case of the chemoattractant, it will leak across that blood vessel barrier and then find itself resting in the outside of that vascular wall, where it is now ready to invade the other tissue portions.
Let's think of the cancer cell like a seed. The seed needs soil in order to become a plant, correct? In this similar vein, the cancer cell that traveled all so far away from the primary tumor cell, the primary tumor, needs the right microenvironment in order to proliferate and become the secondary tumor. It needs the right area and the right nutrients and the right just environment in order to become big. So what is one way that a cancer cell can do this? Let's talk about angiogenesis. Angiogenesis is basically when the cancer cell tells the blood vessels, hey, come grow this way, come grow towards me. And it does that by extruding something called VEGF. VEGF, or vascular endothelial growth factor, is a growth factor that makes the blood vessels grow towards the cancer cell. This is opposed by thrombospondin. Thrombospondin is an anti-angiogenesis agent that tells tells the blood vessels, hey, don't grow that way, don't grow that way. The problem is the cancer cell has a lot more VEGF than thrombospondin. And you can even see these guys are not too happy about it. So the VEGF overpowers and overwhelms the thrombospondin and it reaches the blood vessels. So what's happening over here? Well, the VEGF attaches to the little receptors on the surface of blood vessels. This red is called the basement membrane and the yellow is called the endothelial cells. These endothelial cells line the inside of the blood vessels and they're a very thin coat of cells. So what happens when the VEGF binds to the receptors? It sends like a little message that tells the endothelial cells, and I'm just gonna draw this out for you. It's gonna start creating these little holes in the basement membrane. Now, that's crazy as it is, but what it does after is that it uses that to sort of, the endothelial cells will start forming towards the cancer cell and it'll start building the scaffolding towards the endothelials, towards the cancer cell, right? And we have our, our endothelial cells right here. And it does this with the help of adhesion molecules, which I'm gonna draw right here. These adhesion molecules essentially combine all of the endothelial cells together to make it into a tube in order for the blood vessels to be formed towards it. So I'm going to scroll down and you can see here that the nutrients are going this way normally, but with the addition of this new hole over here, it's gonna start moving towards it. And you can see that the cancer cell now has access to all the nutrients in the blood, and it has made like a diversion from the blood vessel to the cancer cell. This is just one of the ways that a cancer cell can create the perfect microenvironments for itself. Another way is by evading apoptosis. So what is apoptosis? It is basically the programmed cell death, and it tells cells, do not grow anymore, please die. It's the way for the body to regulate its cells, but cancer cells have the ability to block apoptosis. All of this, all in all, I'm saying this to show that cancer cells create the microenvironments for themselves so that they can form a secondary tumor. But not all cancers metastasize. You have to realize that things have to be in the perfect conditions and the perfect settings. So let's talk about treatments. What do we want to do when treating cancer, when treating metastasized cancer? We just want to find the longest survival outcome, the least possible side effects, and the best quality of life. Metastasized cancer is very, very deadly. And the best thing to do is to just make the quality of life better. Another interesting thing is that they're treated based off the original site of the cancer. So if breast cancer is metastasized to the liver, it's treated the same as the breast cancer. So let's talk about different treatment options. We have chemotherapy, which is the use of drugs to destroy cancer cells by growing, dividing, and making more cells. We have radiation therapy, which is using a high energy X-ray to kill the cancer cell. Bob looks very happy shooting that gun, but it's not that simple, But yeah, that's the reason. And there's so many different more variations. There's surgery, hormone therapy, target therapy, and many different other treatments that can be done. But if you're not an oncologist, what can you do to help? donate to St. Jude, the World Cancer Research Foundation, and other cancer websites to raise more money for the research. Well, I will have to say thank you for watching.